Welcome back. This is lecture 9. So we were discussing mm, about transmission lines and how to characterize them, or rather, we are discussing about transmission lines so far and its impact on on uh, on impedance of changing the impedance that one would otherwise see. Right. So putting a transmission line seems like it is changing the impedance, and in the previous lecture we saw the intuitions behind that, and we also did some maths. So in this lecture, what I plan to do is to at least as to motivate as to, if you have a transmission lines which, or rather if you have a long line which seems inevitable in an RF system, where the adjective long essentially means long with respect to the uh, um, wavelength of operation. Uh, so in that case, we need to have a framework to analyze these transmission lines, these long lines, which would probably be slightly different with respect to all the frameworks that we have learned so far in our UG courses, like Z parameters, Y parameters, and so on. Right. So why do we need a different framework? The reason we need a different framework is because what is essentially happening is, when you have this transmission line having certain characteristic impedance and certain delay associated with it, and you terminate this line with any impedance that you want, call it ZL, then looking in here, it is almost never equal to ZL, right? It depends on the frequency, it depends on the length of the line, and so on. So this need not necessarily be equal to ZL. Okay. The other problem is, if we, let's say, try to find out the impedance of an open circuit at line, I might end up getting a short circuit depending upon the, I might end up interpreting it to be a short circuit depending upon the length of the line. And similarly, if that one side is short circuited, I might end up interpreting it like an open circuit depending again on the length of the line. And all this is happening because we have a traveling wave and a reflected wave, and there is a time lag between this traveling wave and the reflected wave, and when these time lag waveforms add up, right, then it is quite possible, depending upon the magnitude of the lag with respect to the time period of the signal, it is quite possible that I end up with a constructive or a destructive interference, right? So essentially, the whole purpose of designing these RF systems is to ensure that we make it reliable in the presence of all these non-idealities, or in the presence of the long lines also, right? So we saw in the end of the last class, one way of ensuring that this happens is to ensure that each point or each interface is terminated with an impedance which is equal to the characteristic impedance of the transmission line. Okay, so now if that is the case, then we need to design a framework in which lines which are terminated, transmission lines or networks which are terminated with the characteristic impedance of the transmission line, have to be analyzed, right? So normally, when we consider one port or two port networks, what type of analysis we normally do? We do either a Z parameter analysis or a Y parameter analysis, right? Now, if I refer to a Z parameter analysis, what is a Z parameter analysis? In a two port network, and I do a Z parameter analysis, what is the assumption? The assumption is, or rather, what are these parameters? The parameters are Z11, Z12, Z21 and Z22. And how do I get these parameters? Z11 is essentially the impedance of the network when the output side is open circuit, right? So if this is V1, this is V2, and this is I1, and this is I2, then Z11 is nothing but V1 over I1 when I2 is equal to 0. That is, output is open circuit, right? So can I use this framework to characterize my transmission line? I mean, obviously we'll get some values of Z11, but it will be of little significance because it will not give us an intuition as to what is happening other than the line. I might get a number, but that number will not have too much of meaning. But the important thing here to note is that Z parameters are characterized with open circuited ports, right? Z parameters are characterized with open circuited ports. What do I mean by that? Just like when you are characterizing Z11, you are open circuiting port 2, that is I2 equal to 0. Similarly, if when you characterize Z22, you would be open circuiting the input port. Similarly, when you are characterizing Z21, right, again you will be open circuited the output port and so on. So similarly, when you do Y parameters, what do? These are characterized with short circuited ports, right? In Y parameters, you have Y11, Y12, Y21, Y22. Just like Z parameters, when you open circuit one port and find out the voltage, and you apply a voltage and find out the current. In Y parameter, what do? You short circuit one port, then you apply a voltage and find out the current, or you can apply current and find out the voltage, but the ratio is that of admittance, right? So okay, so but by now you should be able to appreciate the fact that none of these will be of much use to us, right, if we cannot truly open or short circuit any port, right? And why did I make that statement? I made the statement because how do you short circuit a port? You basically connect a wire between two lines, two points, two terminals of the port, right? And moment you connect a wire at reasonably high frequencies, then you essentially end up getting an inductance. And if you want to open circuit, right? So the port will terminate somewhere, both the terminals will terminate somewhere, and moment you terminate it with anything, you are going to have a capacitance between those two terminals, right? Those capacitance and those inductances are always present, but they are more dominant, their effects are more visible at higher frequencies than lower frequencies, right? Within quotes, higher and lower. So that is why Z parameters and Y parameters can be used to characterize systems which are operating at much lower frequencies than RFICs, right? And so essentially, when you can neither short or open circuit a port, then effectively these parameters are of little use. Other thing is, since we are anyway, the goal is, what is the goal? The goal is to ensure that there is no reflection in any part of the interface in an RF system, which essentially means that we are trying to match every interface to a predefined characteristic impedance, which means just like in a Z parameter, we are characterizing everything with respect to open circuited port, or in case of a Y parameter, we are characterizing everything with respect to a short circuited port. We need another parameter where we will be characterizing the network with respect to its matched ports, right? So we need a parameter to characterize a network when it is terminated with the characteristic impedance of the line, right? So this is the need of the day, okay? And also the so this definitely is the need of the day. And the second need of the day is, what is the whole major reason of this? Again, I'm repeating myself. What is the major reason of this impedance, seeming the impedance change that is happening when you have long line? The reason is essentially you have forward going wave and reflected wave, right? That is causing all these problems. So second need is, we need a way of, so the parameters should be able to characterize the incident and the reflected waves also, right? Okay, so as long as we are doing everything on pen and paper, it is easy to come up with any parameters, right? So you can come up with your own parameters tomorrow. All you need to do is to be consistent with the framework that you choose. So the frameworks that people much smarter than us chose years back is that of saying that we have a network, we have a two-port network, right? And we know that there will be waves which will be impinging on them. We call, let's say, waves which are incident in port 1, I call it V1 plus. Waves that are reflected from port 1, I call it V1 minus. Similarly, waves that is incident on port 2, note the direction, right? That is going in to the port 2, we call it V2 plus, and one that is reflected out of port 2, we call it V2 minus, right? So then all we need to do is to ensure that the parameters capture this plus and minus things, right? And secondly, we have to ensure that whatever parameters we come up with should be able to capture the effect of matching or not, right? Okay, so so essentially, what do you want? So the people who came up with characterizing these V plus and V minus waveforms, and this is how they do it. So let's say I am interested, the goal is to, again, the goal is to minimize reflection. So what should the parameters capture? Parameters should capture reflected wave should be equal to some function of incident waves, right? So essentially, what are the reflected waves? Reflected waves are V1 minus and V2 minus, right? And what is the incident wave? They are V1 plus and V2 plus. So essentially, if everything is a linear time invariant network, I can basically say this is a linear combination of V1 plus and V2 plus. So I can basically say this is some V1 plus and V2 plus. So I'll have something here plus something here. Whatever is prefix to V1 plus, we'll call this S11, just like we called Z11, Y11. Whatever is prefixed in front of V2 plus, this will be S12. Similarly, here we are going to get S21, here we are going to get, okay. So in a more compact form, these are often referred to as in the form of matrices, just like we refer Z parameters and Y parameters in terms of matrices. Sorry, it should be V1 plus. Okay, so again, let me redraw. Okay, so by definition, then what is just like when you characterize, when you start developing any parameters, you have to define those parameters also. So what is if I rewrite, so V1 minus this equal to S11 V1 plus S12 V2 plus. So what is S11? S11, I can say S11 is equal to V1 minus by V1 plus when V2 plus is equal to 0, right. So if I set V2 plus equal to 0, the ratio of V1 minus and V1 plus is essentially S11, right. This is similar to again Z parameters, right. When you just like Z11 is input voltage by input current when the output current is 0. Similarly here it essentially means that uh, S11 is V1 minus by V1 plus when V2 plus is essentially okay. So now what is meant by uh, V2 plus to be essentially 0? So what is meant by V2 plus to be equal to 0? So you have to be careful with the notations here. So note that uh, we have we have denoted the plus signs as the signals going into the port. Okay, but if you assume that there is a each of these lines that are coming out, they are like transmission lines, which are long lines. That is the whole purpose of doing S parameters. Each of these lines have a characteristic impedance Z naught, and they are associated with a time tau, right? So when I say V2 plus is equal to 0, what does it mean? So in this setup, it looks like your V1 plus is the independent variable, right? And we are trying to characterize the system with respect to V1 plus. When I say V1 plus is an independent variable, what does it mean in terms of circuit? It essentially means that there is probably a source that is connected, which is providing the V1 plus, right. So there is a source connected on the left hand side in this diagram. There is a source connected, and that is pushing in the V1 plus, right. And the assumption is that the output you are probably taking from other side, that is the port 2, right. So what is the signal direction of flow? So the flow direction is from here to there. I should use a different color. the flow is from this port to that port. Okay, so what I essentially am trying to motivate is, so your signal is coming into port 1 and going out of port 2. So when you say, so signal is in the port 2, this is coming in this direction. So when I say with respect to the direction that I showed, right, with respect to the direction that I showed, uh, and by definition, what are we trying to ensure? We are trying to ensure V2 minus is essentially 0. I'm sorry, what I'm trying to, uh, I'll take the statement back. What we are trying to say is that whatever is going out is fine, but whatever is coming in to port 2 should be 0, right? So V2 plus should be equal to 0. Okay, so this essentially, by this, what we are trying to impose, we are trying to impose that there should be no reflections at the load interface. Why do I say load interface? Because after the two-port network, you are going to put a load, right? If you keep it open, V2 plus will never be equal to 0. Something is going to come back. Okay, so how do you ensure that there is no reflection at the load interface? You have to terminate with a matched load, right? So you have to terminate with an R which is equal to Z0. Okay, so this essentially means that, i.e., port 2 is terminated with Z0, right? So now, do you see that by definition these S parameters captures our requirement, in the sense that the S parameters are this new parameter which we are calling the S parameters are capturing the the essence of reflections from interfaces, and also it is also, in order to characterize these ports, we'll have to terminate one or the other port with matched load, right? So these are essentially referred with respect to a matched impedance, not an open circuited impedance, neither a short circuit impedance. Okay, so now let's complete the definitions. So you have minus V2 minus equal to, so again, what is by definition of S11? S11 is reflection at the input port when the output port is terminated with a 50 ohm load, right? So output port is matched. What is the definition of S22? S22 will be what? S22 will be V2 minus divided by V2 plus, right? When the input port is, when there is no reflection at the input port, right? So again, go back to this. What is S22? S22 is V2 minus divided by V2 plus when V1 plus is equal to 0. And how do I ensure V1 plus is 0? Which means there is no reflection at the source interface, right? So this is essentially V2 minus over V2 plus when input port is matched. Or I can also say this, no reflection at load interface. I can also say this to be as no reflection at source interface. Correct? Similarly, I can characterize S12. So again, go back here. What is S12? S12 is V1 minus by V2 plus when V1 plus equal to 0. So let's write it down. So V1 minus over, here I made a mistake. V1 minus over V2 plus when the input port is matched, right? So V1 plus equal to 0, i.e. input port is matched. Okay, and similarly S21 is V2 plus or V2 minus by V1 plus when V2 plus equal to 0, i.e. output port is matched. Okay, so the moot point is that if you have to characterize these S parameters, you have to do 4 different sets of experiments, right, in hardware. In 2 setups, you will have to apply. So these are those inevitable long transmission lines. In one setup, you will have to apply an input by the way, since we are talking about matched interfaces, right? So the assumption is that the input also has a resistance associated with it, which is matched to the characteristic impedance, right? So you apply. So let me do one step at a time. So terminate the output port with Z0, right? So this setup can be used to characterize. In this case, there is no reflection at this interface. So essentially this V2 plus is equal to 0. So can be used to cap which two S parameters? V2 plus is equal to 0 is essentially S12, right, and at S2, sorry, S21 and S22, right, can be used to characterize S11 and S21. Okay, and how are you going to characterize? You need V1 plus, right, because everything is with respect to V1 plus. You need this V1 plus. This is not going to come if you leave the input port open circuited. So how do you apply a V1 plus? So you have to apply a V1 plus obviously through a voltage source, right? And the voltage source should also have a resistance which is the same as the characteristic impedance of the transmission line, because otherwise you are going to have again, so this is R equal to Z0. Okay, so this can be used to characterize S11 and S21, and the What character setup would you like to use to characterize the other two parameters? So you basically then for the other two parameters you terminate the input port with Z naught and apply input at the other port, right, which is also connected to the uh, uh, connected to the port. Okay, okay. So now let's do couple of examples that will probably help us understand the help motivate the reasons behind doing all these things. Okay, so let's start off with a single port network example, which is fairly simple, uh, and hopefully that will show you how the analysis or how the S parameters can come to our rescue. So let's assume that I want to characterize there is a capacitor. Okay, let me take a real example. Let's say I have a common source amplifier. I'm not showing the biasing, and let's assume we are only interested in the incremental models, right? Uh, okay, and there is a long transmission line, and I have an input EI R not equal to R connected here, and the output is again taken out through a long transmission line connected here to R, right? Okay, these taus need not be the same, but without loss of generality, for the time being, we can assume that. Now, we understand that this common source amplifier at a very simplistic format gives and has an input capacitance, right? So essentially, this is a capacitor C, and I would like to understand what is the value of this capacitance, and I choose to do a Z parameter analysis. Then what do I end up with? If I choose to do a Z parameter analysis, I will see that there is a V1 plus. This V1 plus will come all the way here, and I will get V1 plus e to the power minus j omega tau. I'll have some reflection, gamma c, V1 plus e to the power minus j omega tau, and this reflection will appear here as gamma c. It is V1 minus will be gamma c, V1 plus e to the power minus 2 j omega tau. Correct? So what will be the total voltage at uh, port 1? So note that this is my port definition, right? So this is port 1, and this is port 1. And this is port 2. Okay. Now note that I called at the beginning, I called this a single port network. This is actually not a single port network, it is two ports. But if port 1 and port 2, there is no direct interaction between port 1 and port 2, there is no feed through, right? So then I can basically say that port 1 is isolated from port 2. Port 1 influences port 2, but port 2 does not influence port 1. I mean, that's the way I set the problem up. And if I only now characterize port 1, right, so then I can, it's as good as saying that it's a single port network, right? But in the truest of sense, you have two ports. Okay, so if I characterize this for S11, if I characterize this to find out the input impedance, what I'm going to see? So input impedance will be nothing but Z in that is looking in impedance here, Z in will be nothing but the total voltage by total current going into the board. So what is the total voltage? That is the reflected plus incident waves voltages. So that is nothing but V1 plus 1 plus gamma c e power minus j 2 omega tau, right? And what is the current? Current is, incident current is V1 plus by Z naught, reflected current is V1 minus by Z naught, and the incident current minus the reflected current, right? So essentially this becomes Z naught times 1 minus gamma c power minus j 2 omega tau, right? Now what is oh sorry, this v1 plus will cancel because, right? So essentially this becomes Z naught times, now by the way, what is gamma c? Gamma c is basically the reflection coefficient at the capacitor interface, which is nothing but 1 by j omega c minus Z naught by 1 plus 1 by j omega c plus Z naught, which is 1 minus Z naught, but Z naught is a real impedance, or Z naught is a real impedance. That's the assumption. Z j Z naught omega c by 1 plus j Z naught omega c, right? Now note that mod of this is equal to 1, right? This quantity, and but it will have a phase, so I can simply write it as e power minus j or 2 phi, where phi c is equal to tan inverse of Z naught omega c, right? So this is your gamma c. So from there, if I have to plug in these values into Zin, what do I get in Zin? Zin becomes 1 plus e power minus j 2 phi, so I can have 2 common, 2 phi plus omega tau by 1 minus e to the power minus j 2 phi plus omega tau, right? So what is this telling us? This is essentially telling us this impedance can be anything, right? Depending upon what is omega t or plus phi, it can be 0, it can be infinite, it can even be real, right? So so at different frequencies and for different length of the transmission lines, right? So this, just observing Zin when you have a long line associated with a long delay is useless. That we already knew, but this gives you a mathematical framework of understanding why this is happening. But how does S parameters help us? The S parameters help us in this way, that if I now see, and I want to characterize this, only the input impedance, what am I looking for? I'm essentially looking for S11, which is V1 minus by V1 plus when V2 plus is equal to 0. So under this setup, what is V2 plus? V2 plus is this, right? Is the V2 plus 0? Yes, V2 plus is 0, right? Because I have forced the output port to be at Z0, right? So if since V2 plus is equal to 0, all we have to do is find out what is V1 minus and what is V1 plus. That we have already figured out from the previous analysis. So this is V1 plus, this is V1 minus. So this is our V1 minus, and this is V1 plus. So ratio of that is nothing but gamma c e to the power minus j 2 omega tau. Okay, so uh, which essentially means that uh, tau c or gamma c, which is equal to, I am replacing c with zl for the time being, zc, just to keep things slightly generic. Zc minus z naught by zc plus z naught is essentially S11 e to the power j 2 omega tau, which essentially means your zc nothing but zl times 1 plus S11 e to the power j 2 omega tau by 1 minus S11 e to the power j 2 omega, right? So note that if this is a much simpler way of finding out what your characteristic, what your effective impedance is, because I'm messing up the notations, right? Because z naught is known a priori, right? Uh, the tau, if you know the length of the line, then you know tau, right? So that is also known a priori, and S11 you are measuring, right? You are measuring, if you can measure S11, right? There are, I mean, obviously there is no point in coming up with a parameter which you cannot measure. Let's assume that you can measure S11. If we can measure S11, then you can simply plug in these values and we get z naught, right? Uh, Now, I mean, one might say if I know tau and one might know, I know all these things, I can find out z in from this equation also. Yeah, sure, you can, but as you can see that this is far lesser of a job than the other one, right? And also it is not only for for analysis purposes. I will talk about why terminating with matched impedance has significant practical usage also, not for synthesis purpose, for design purposes also, right? Other than the reflection part that I talked about. Okay, fine. So now let's say I want in the same network, I want to find out. So this is as far as S11 is concerned. We can similarly do the others. We can let's quickly go through the others. Uh, what about uh, what about S12? What is the definition of S12? S12, again, let's go back. S12 is V1 minus by V2 plus when input port is matched, right? So V1 minus by V2 plus input is matched, right? So we probably don't need to do much about this, because what is the setup? The setup is okay. So let's assume that we have a V2 plus and we are trying to find out V1 minus. What is V1 minus? V1 minus is this. Okay. So input is matched, means this is connected to Z0. And note that for this analysis, all it is sufficient for us to get V2 plus. I did not apply a voltage source for the analysis purpose. But when you are actually doing an experiment, you have to connect a voltage source. Okay, fine. So in this case, since we have assumed an unilateral device, there is no way signal can flow from this side to that side, right? So essentially your V1 minus will be equal to 0. So easy. So this will be effectively equal to 0. What about S21? What is the setup for S21? In S21, what are we doing? S21, we are applying an input at the input port, and at the port 2, we are observing the output when port 2 is matched, right? So essentially this setup, right? So so what will be your S21? How do we find out what is S21? So essentially I'll have to find out what is the current that is going in, right? And whatever current goes into the R, right? If the current is a function of V1 plus, then we are good, right? So what will be the current here? The current will be nothing but the direction I have shown. Let me write out. Maybe I'll copy this setup. Do not have enough space there. So in order to find out this output current, by the way, we are interested in V1, V2 minus. So that is we are interested in this, right? Output is anyway terminated with a characteristic load impedance, so which there is no reflection from the output side. So if I have to find out this V2 minus, I will essentially need to find out what is the current that is coming out of this transistor, and I know that this current is GM. This current is GM times VGS, where VGS is this is the total VGS, right? So for this I need to find out the total voltage across the capacitor. So what is the total voltage across the capacitor? That we have already found out in our previous analysis. Right? The total voltage of the capacitor is V1 plus e power minus j omega tau, and there is a reflection, that is gamma c times V1 plus e to the power minus j omega tau, right? So essentially this is equal to V1 plus e power minus j omega tau 1 plus gamma c, right? So this is so your output current is GM times VGS, which essentially means that the voltage at the output V0 is minus GM times VGS times R, and V2 minus is negative of that, right? Because simply I'm sorry, V0 is essentially equal to V2 minus. We know that V2 minus is equal to V0, right? Because there is no reflection at the output port. So V0 is essentially V2 plus V2 minus. Since this is essentially 0, V0 becomes essentially V2 minus. So your S21, which is V2 minus over V1 plus, essentially becomes V2 minus is how much? Minus GM VGS, which is V1 plus minus j omega tau 1 plus gamma c by V1 plus cancels. So your S21 becomes minus GM times e power minus j omega tau 1 plus gamma c. What about S22? The final thing that remains is S22. Which setup are you going to use for S22? So essentially, we are going to use this setup. And what is our S22 definition? is basically characterizing the reflection at the output port. So that is nothing but this is V minus, nothing but V2 minus over V2 plus. And note that the way it has been set up, output input, this is basically open circuit, right? If you assume that there is some capacitance, the expression becomes identical to that whatever we I mean, similar to that of S11, but the way we have set it up, we have assumed it's an open circuit. So this is open circuit, right? So V2 plus goes, it's the open circuit, it's a round trip delay and comes back. So your V2 minus is nothing but V2 plus 1 plus e power minus j 2 omega tau by V2 plus, right? So this goes, your S22 essentially becomes 1 plus e power minus j 2 omega tau. Okay, so you see that, I mean, mm, so this is a way of finding, I mean, uh, this is a toy example that we use to show you how do you go about characterizing a S parameters of a two-port network. Before we end today's lecture, there is something that I would like to point out, that when you use, let's say, a simulator to characterize, to find out S21, S11 and all those things, all those parameters, then you have to be careful about one important thing, and that thing is the following. So let's say this is my input, I have a resistance R, and there is a connected to a transmission line of Z0, which is equal to R. Okay, and you have, you consider the same, I mean, consider the setup in which I have some connection here, some load which is RL. Okay, so what is V1 plus? If you go back to the previous lecture, you are going to see V1 plus essentially is equal to Vi by 2, right? Because what? Because of what reason? Because at this interface, right, when the forward going wave gets launched from Vi, right, it sees a matched load, it sees a matched termination, it doesn't know what is connected to the other side of the transmission line, right? It is just the wave is just entering, wave is just entering a transmission line. It doesn't know what's connected to the other side until and unless it goes and finds out something, some non-matched load, it cannot come back, right? So as far as the forward going wave is concerned, right, it essentially always sees a matched impedance. Note that this is the so I should say forward going or incident wave, because incident wave sees a matched interface, right? Note that this is not the same as saying that interface is matched in totality, right? So this is not same as saying Zin is matched, because Zin is essentially total voltage by total current. Okay, so that is point number one that you should keep in mind. Now, the point number two that you should keep in mind is sometimes. So what is S21? So S21 is nothing but V2 minus by V1 plus when output is matched. Okay. So in some cases when the output is uh, let's say your input is not matched but your output is matched, right? So let's assume your input is not matched. When I say the input is not matched, what I essentially mean, let's say this is R and you have a transmission line with Z naught is, let's say, is greater than R. Okay. And you have an output terminal Z naught which is matched. Okay. So here when you do an S1, when you find an S21 for this, so I will leave it to you. So find S21. So when you go ahead and find an S21 for this S21 will be higher than that you will get in when Z naught is equal to R, right? So this S21 will be higher than what you will get when Z naught is equal to R. That does not necessarily mean it's a good design. S21 essentially is a gain, it's a voltage gain, right? It might give you a feeling that you have suddenly got something with a higher gain. You have got it, but it did not necessarily be a good idea because you have done it as a while sacrificing the input match, right? So input match sacrificed, right? So sometimes you will have to be careful that uh, you might get a larger S21, right? But if you get a larger S21, you also will have to go back once to do a sanity check of S11 also, right? So the key takeaway is always check S21, always check S11 while designing for S21 also, right? So this is something that you should keep in mind because I mean you might sometimes get erroneously fooled into thinking that suddenly I have higher S21 means I have higher gain, right? You indeed have higher gain, but that design probably will not be useful simply because uh, you have done it by sacrificing the input match. Okay, okay.